Now recall from the beginning of this section, we defined the topology on the ring of periodic integers Zp as follows. We first give each an, where an is Z mod Pnz, the discrete topology, and Zp inherits the subspace topology from the product topology on this infinite product of ans. By Tikhonov theorem, this infinite product is compact because each factor is compact. And we showed that Zp is closed in this infinite product, and the subspace topology is also compact. In the next proposition, we are going to define a metric on Zp. And we will show that the metric topology is the same as the subspace topology inherited from the infinite product. The topology on Zp can be defined by the distance. For x and y in Zp, the distance is defined as e to the power negative the periodic valuation of x minus y. And under this metric or distance, the ring Zp is a complete metric space in which Z is dense. What do we mean by Z is dense here? We mean that Z can be naturally embedded into Zp by sending an integer here to Zp, where all components are represented by the same integer. And we will explain this in more details in the proof. Now let's prove this. First, we will check that this d indeed gives a distance or metric on Zp. It is clear that d of xy is equal to d of yx. This is because if x minus y has a periodic factorization p to the n times u, then by the unique factorization of periodic integers, we have y minus x is equal to p to the n for the same n times negative u. Because u is invertible if and only if negative u is invertible. And as a consequence, d of x comma y is the same as d of y comma x. And second, d of x comma y is equal to 0 if and only if x is equal to y. This is also clear because d of x comma y equals 0 happens if and only if this v sub p of x minus y is equal to infinity. And vp of x minus y being infinity happens if and only if x minus y is equal to 0 or x equals y. So this is also clear. Now it suffices to verify the triangular inequality for this distance d. To this end, we take 3 points in the ring of periodic integers. And we want to show that the distance between x and z is less than or equal to the sum of distances from x to y and y to z. First, we're going to write this by definition as e to the power negative vp of x minus z. And we break this into 2 parts. as the sum of x minus y and y minus z. Now we're going to use the second property for the valuation, saying that the periodic valuation of x plus y is bigger or equal to the minimum of individual periodic evaluations. And it follows that this guy is less than or equal to e to the power negative the minimum of Vp of x minus y and Vp of y minus z. And this guy, written in another way, is the maximum of e to the negative Vp x minus y and the e to the power minus Vp of y minus z, which by definition is the maximum of the distance between x and y and the distance between y and z. And this last guy is less than or equal to d of x comma y and d of y comma z. And here, we are actually showing something that is stronger than the regular triangle inequality. We are showing that for any x, y, and z, the distance between x and z is less than or equal to the maximum of the distance between x and y and distance between y and z. This part is called the ultrametric inequality, which makes this metric space a ultrametric space. But for the moment, we do not use this notion. So let us just stay with this triangular inequality. Anyways, we have verified that d of xy indeed defines a distance on ZP. And this verifies the claim. And now we are going to show that the topology defined by this distance is same as the subspace topology we defined from the beginning. And to this end, we're going to study the neighborhood basis on ZP. The first thing we are going to show here is that if we consider the ideals in ZP of the form PNZP, we will claim that these ideals form a basis of neighborhoods of 0. This claim itself has nothing to do with the metric. But after showing this claim, we will translate this into the language of periodic valuation and metric. So let's check this claim. And let me emphasize, we are only talking about the subspace topology here. And we are going to make a subclaim. We will check that p to the n times ZP is equal to the intersection of ZP with the product of y case, where yk is equal to 0 for k between 1 and n, and ak for k bigger than n. And because ak's are endowed with the discrete topology, and each of them is a finite space. So those singletons are closed and open sets in AK. And those singletons are closed and open sets for k between 1 and n. Therefore, this product of YKs is actually an open subset in the product of ANs. And to check this subclaim, we first observe that this containment is clear. Because clearly, p to the n times zp is contained in zp. And because p to the n also kills the first n components of the elements in zp, so this guy is also in this infinite product. So this part is clear. For this direction, we take an arbitrary element from the right-hand side. And we observe that the theta y lives in the kernel of epsilon sub n. Where this epsilon sub n is a projection of elements in zp onto their nth component. If you don't remember, this was defined on page 11 before proposition 1. Now clearly, y is in the kernel of this map because the nth component is equal to 0. Now by the proposition 1, we know that the sequence ZP is an exact sequence, meaning the kernel of epsilon sub n is equal to the image of the multiplication by Pn map. So as a consequence, we can write y equal to p to the power n times y prime, where y prime is in zp. So y is in p to the power n times zp. This is what we need for this subclaim. And as a consequence, we have that p to the power n times zp is open in zp. Recall that in this main claim, we want to show those ideals form a basis of neighborhoods of 0 in zp. What we want to do now is that we want to show that for any open subset in zp containing 0, it must contain some p to the n times zp. Now we take an open neighborhood of 0 in zp. But the definition of product topology, we know it contains some neighborhood 0 with the following form. It will contain some zp intersection, the infinite product of xk's, where all but finite many xk is equal to ak. But clearly, from this construction in this subclaim, we know that this infinite product of sk's must contain some infinite product of yk's for some n. Where this infinite product of yk's is precisely as defined from here. To be rigorous, I should put some superscript n here to indicate there's a truncation at the end. But for the simplicity of notations, I'm not making that superscript. But it is clear from this argument here, you know that because all but finite many xk is equal to ak, and this infinite product contains the zero element, meaning the infinite vector 0, 0, 0, 0, 0. This infinite product of xk must contain a product of this form for sufficient large n. And therefore, p to the n zp is contained in zp intersection this infinite product of sk's for some large n. And because any open neighborhood 0 in ZP contains a set of this form, and the set of this form must contain P and ZP for some large n, we know that any open neighborhood 0 must contain some P to the n times ZP. And this shows P and ZP's form a basis of neighborhood 0 in ZP. And the verification for P and ZP's being ideals is straightforward. Because if you take any element in ZP and element here, their product must also be the form Pn times some element in ZP. So this verifies this claim. Now we are going to translate this into the language of p-adic evaluations. We first make an observation. We observe that an element lives in PNZP if and only if the p-adic evaluation of this element is bigger or equal to n. This simply follows from the same argument that we gave here by the proof of proposition 2, part B. This is on the page 12 of Sarah's book. In that proof, the p-adic evaluation is the largest integer such that the component of x at that integer's position is equal to 0. And x living in p to the power n times zp means the first n components of x must vanish, which is the same as saying the p-adic evaluation of x is bigger or equal to n. And now we're going to show that the topology on ZP is actually defined by the metric e to the power minus VP of x minus y. Or in other words, the metric topology coincides with the subspace topology. To check this, we know that we have just shown that p to the power n zp form a neighborhood basis of zp at 0. Now, translating those sets by x in zp, we have that p and zp plus x form a neighborhood basis of zp at x. And now take any open set V in ZP and any point X in V. We know by the definition of neighborhood basis that V contains some Pn ZP plus X. Now, since an element living in Pn ZP plus X is equivalent to y minus x living in Pn ZP, which is equivalent to, by our observation here, the periodic valuation of y minus x is bigger to n, which, by the definition of the periodic distance, d of xy is less than or equal to e to the minus n. Therefore, the set Pn(ZP) plus x is equal to the closed ball under this metric. This means the set of elements whose distance to x is less than or equal to e to the negative n. And this guy contains the open ball centered at x with radius e to the negative n. This set means all the elements whose distance to x is strictly less than e to the minus n. Therefore, we have shown that any open set in ZP can be written as a union of open balls in this metric. And this shows that the metric topology contains the subspace topology, because any open set here is also an open set here, because any union of open sets is an open set, which is one of the axioms for topology. Now, on the other hand, for any open subset V metric in ZP with respect to the metric D and any x in V metric. By the definition of metric topology, we know there exists an epsilon bigger than 0 such that the open ball centered at x with radius epsilon is contained in V metric. Now, there exists n bigger equal to 1 such that e to the negative n is less than epsilon. And it follows that BD x epsilon, this ball with radius epsilon, contains the set p to the power n times ZP plus x. Because the elements here are precisely those whose distances to x is less than or equal to e to the negative n, which is less than epsilon. So this ball contains this set for this set. But we know that those sets will form a neighborhood basis for x. So the argument above shows that this V submetric can also be written as a union of open subsets in the subspace topology, because this neighborhood basis is for the subspace topology, as we argued from the beginning. So this shows the metric topology on ZP is contained in the subspace topology on ZP. So two topologies agree with each other. Now, for proposition number 3, we have verified the topology can be defined by this distance. And it follows immediately that the ring ZP is a complete metric space. We have shown that from very beginning, when we define ZP and its topology, that ZP is compact. Now we have just shown that the topology here agrees with the metric topology. Now it is a compact metric space and therefore complete. Finally, we will show the following. We will show that the closure of integers is equal to ZP. Namely, Z is dense in ZP. But here, I need to clarify how do we put Z inside ZP. We embed Z in ZP by sending an integer L to the infinite vector where all components are equal to L. So this is the embedding. To verify this, we make the following claim. If X lives in ZP, and if the sequence Yn is in Z, satisfying that Yn is congruent to Xn modulo Pn, then the limit with all components represented by the same integer indexed by this n is equal to x, where x is this. And here we embed this element into ZP. So we regard this guy as an element in ZP. The compatibility is clear because they are all represented by the same integer Yn. It follows immediately from this claim that Z is dense in ZP. Because for any element in ZP, we have found a sequence in Z embedded into ZP whose limit is equal to x. And now let us check this claim. And we are done. Since by construction, Yn is congruent to Xn modulo Pn. Remember, this is the same as saying that the Yn is equal to Xn regarded as two elements in An. Now we're going to use the compatibility. And we're going to apply the map phi sub n to both sides. And we get an equality in An minus 1. And now by the construction, the left-hand side, which is the element next to this, is still Yn. But the right-hand side is x sub n minus 1. So if you look at this equation in the ring of integers Z, it translates to Yn congruent to Xn minus 1 modulo Pn minus 1. You can either use this language or this language. Both are fine. And now we repeat this procedure by applying phi sub n minus 1, phi sub n minus 2, all the way to any integer phi sub m. And eventually we will have yn equal to xm in a sub m, or using a language in Z, yn congruent to xm modulo pm. This is for any m from 1 to n. Therefore, if we take the difference between these two elements, we will have an element in ZP whose first n components are all equal to 0 because of this. And starting from the n plus 1's position, we could have non-zero terms. And this guy is equal to p to the power n plus 1 times some element u. But this u may or may not be divisible by p. The thing on the left is our y, and the thing on the right is our x. Translating this in terms of the language of periodic evaluations or periodic distance, we have that Vp of yn minus x is bigger to n plus 1, or in other words, the periodic distance between yn and x is less than or equal to e to the power negative n plus 1. Taking limit, this shows that the yn converges to x as n goes to infinity. And this verifies this claim, and therefore the whole proof.